Hmm. Are you there, Tiara? Dion, you there? Ugh. Ah, there you are. And there's Dion. Dion and Tiara, Except Tiara's gone out of the picture. Okay. All right. Did you guys have a good weekend? What'd you do, Dion?
Nothing.
Nothing. That made it a good weekend, right? Okay. All right, let's see. Who I got next? Okay, there's Deborah. And there's probably Alexis. All right, we're all here. Okay. Let's see here. See what I can get. Whoop. There's gallery view, blah, blah, blah. Okay, everybody's here. Oh man, look at Alexis' hair. She got it done this weekend. All right. Yeah. Were you happy with it?
Yeah, I'm very happy with it.
It looks good. It's
Look at
long.
what I got. That's what I was gonna show you.
Look, turn around. I'll see how long it is. Oh God, what's that? Oh my God, you got a black. Is that a chalkboard in your room?
It's a tapestry.
Oh, that's beautiful. Who did that?
Amazon.
Oh, it looks good. Did you just order it?
Yeah, I ordered it because I wanted to get something that represent like my major and my minor.
Yeah, and made you feel like you were at school, in your in your bedroom.
I'm too scared to get a tattoo, so.
Yeah, you can do like a tattoo. Like my friend used to get tattoos in places where you couldn't see them, like under her watch and on the back of her neck, and she's got long hair. And I'm like, well, what's the point of getting a tattoo if you can't see it? But then again, people get tattoos in all kinds of places where you can't see it. So whatever. Okay. So so how are things going, guys, in general?
School's almost over.
School's what?
School's almost over.
Yeah.
I'm excited. I'm ready for summer, get rejuvenated.
Yeah. What are you doing, Deborah? You'll be Are you going to work all summer?
Probably. I'm not working right now because I fell out of a tree.
What? Say that again.
I fell out of a tree the other day, so I'm not working right now. But
number one, what were you doing in a tree? And number two, how'd you fall out?
So it's my birthday, so we went in the backyard to have a piñata. So I was climbing a tree, like, just climbing around, and then a branch broke, and I like landed on the ground.
And what did you hurt?
My knees.
Oh, did you have to go to the doctor?
No, well, they called the ambulance because I was like lightheaded at first, but then I was fine after that. Like I was fine by the time they got there. So.
All right. Well, was that your birthday? Did you say that was your birthday? Well, happy birthday.
Yeah.
The thing you're going to remember about this birthday is that you fell out of a tree, but
yeah.
Okay. Tiara, what you been doing? Thought she's not listening to me. Tiara, now you hear me? What you been doing? Huh? Answer me. Get that mute off.
I've been doing nothing.
So everybody been doing nothing. Golly, I spent my weekend doing nothing.
I did something.
Yeah, well, nothing is something, actually. That's a good thing. You go for a walk or do something.
I tried to make a smoothie and I failed.
What did you try to make it out of?
Some berries, and some other stuff from YouTube. It didn't really work out.
Do you have a blender kind of thing?
Mm-hmm.
You got a blender to fix it in? Is that what you were trying to fix it in?
Yeah. It just tastes really bad, at least to me.
Well, the key, well, that's after I put like yogurt in it, and then I put honey in it.
I did that.
Yeah, and
It
then
still was nasty.
and then what kind of fruit?
Water, and
But the fruit was frozen, so it was like the water and stuff was coming from that, and I was just like,
Yeah, it's better if you get fresh fruit, and I like blueberries best.
I had blueberries, you know?
See? Blueberries and strawberries are the best. So,
I had that too.
okay, so guys, let me share the screen and let's talk about what you have questions on and what's coming up here. Okay, so guys, if by my reckoning here, we have done section 11.4, no wait, 11.5 was the one where we had alternating series, absolute convergence, conditional convergence. There were a lot of problems on that page, and I'd ask you to kind of look at those and see if you see what you could do with those. So I want to know if you had any questions about the homework. These are the kinds of things that you got to do. You got to practice on if you're gonna get them. If you're gonna get good at them. So sort of like integrals. Anybody have anything they had a question about? All right, I'm gonna see how you're doing on them tonight. I've got, if you look on Moodle, there's a quiz on there that says alternating series test. It also says ratio test. Remember, the ratio test was one that we used for absolute convergence. So it's not a very long test, and I've told you what to do on a couple of them, but on a couple of them, you're gonna have to decide for yourself. So what I want you to do is work on those. I think it's only about, it might be 5 problems, maybe, but it's on Moodle. Look at that. I'd like to have it tomorrow before class. All right, and we'll see how that's going. Okay. Any questions on what you'll see when you get on Moodle, guys? A couple of things you'll see. The week 5 syllabus, what we're going to do for the next 5 days. You'll see that quiz, and you'll see another quiz that's coming up. What I'm going to do on this last stuff is sort of have some successive quizzes, because we're getting towards the end here. I know how things go at the end. Things kind of fall through the cracks, so I'm going to try to make sure we get a little bit of everything done. Okay. All right. Questions? Anybody? All right, I'm going to start sort of over with power series. I think I had power series on the syllabus for Friday of last week, but I didn't get as much done as I wanted to. So I'm going to show you, I'm going to start all over with power series, and that's actually a good thing, because we'll get some practice on the ratio test and some different things that work on other things. But let me first start by reiterating, and you might already have this in your notes, but it's what a power series is. What we've been working with in that 11.5 is series that they didn't have any variables in them. All right, they just had, whatever was in there, just the n, and you had to test it to see if it converged or diverged or whatever. In a power series, we end up having something with a variable in it, and the question is going to be, for what values of x will this converge? So that right there says let x be a variable. A power series in x is a series of the form the sum from n equals 0 to infinity of a n x to the n. A n is just a number, some number. X to the n is just an x. We don't know what it is. All right. And the thing you're going to try to find out is for what values of x would this thing converge. So, for example, if I had a power series that looked like this, suppose I had 3 and I had 1/2 to the nth. In other words, my a sub an is just the constant 3, okay? And my x is 1/2. Now, can you tell me what kind of series that is, guys?
Geometric.
It's geometric, isn't it? And the R is less than 1. So what would happen there is that if X was that value, this thing would converge, okay? And we know what the sum was. It's whatever A is, whatever the first term is, depending on where we started. We could start at n equals 0 to infinity, wherever. Then it would look like the first term would be 3. The next term would be 3 halves. The next term would be 3/4, and so on. We could see that R was definitely a half and A was 3, and we could find the sum. So if, on the other hand, I put X equal 2 in this thing, and I had something that looked like this, actually, we'll just put a 3 in that spot again. Doesn't matter what that is. I could pull it out. But if I had a 2, then you say, you know, that looks like it's geometric too. And it is, but the absolute R is 2, and the absolute value of 2 is bigger than 1, so that one would diverge. So if you're just looking at this thing, is there a way we can figure out what values, not just pick and choose them, but what values make this thing converge? Okay, so that's what we're trying to do. So our goal is to find out for what values the power series converges, right there. Okay, now let me say one other thing, a couple of things that are fairly easy to see. If X is 0, the power series is going to converge, because if you take a look at this thing, if you let X be 0, you just get a string of zeros. And if you look at the sequence of partial sums, it would just be 0, 0, 0. The limit of that's 0. So if A0 is the first term, S1, remember when I said sequence of partial sums, I would say, well, if n is 0, if n is 0, I would get A0x to the 0, A0x to the 0, which would be A0. If it would be 1, I'd have A1x to the first, and so on. You can see here that if X was 0, all of these terms drop out, okay? And the sequence of partial sums, the first one's going to be A0. The next one's going to be A0 plus 0. Then A0 plus 0 plus 0. It definitely converges to A0, okay? It definitely converges to whatever that first term is there. So if X equals 0, I don't have much to do. It converges, okay? On the other hand, what if X is not 0? So if you look at this thing in general, guys, it looks like a geometric series. It's just what I was making it out to be a minute ago, because when you write out the terms, you'll get, you know, again, if n is 0, you'll get X to the 0 is 1, the next one's X squared, R is X. Your A0 is 1, so it's geometric. The sum would be A over 1 minus R, which is A over 1 minus X, and it's going to converge if your R, which in this case is the absolute value of X, is less than 1. Now, let's first of all, let's talk about what that means. So if you see something like this, it's going to converge if the absolute value of that X, the thing that R is less than 1. So actually, if I look at this piece right here, all that means is that X is in between 1 and minus 1. Okay, X is in between 1 and minus 1. And remember the ones I picked? The one above here that I picked, which was 1/2, that's definitely between minus 1 and 1. 2 was not. It's going to diverge in those other places, all right? Because we know that's what a geometric series does. So if I looked at one like this, then I could say it's 1 over, I could rewrite it, or I could write out some of the terms. The terms look like 1 plus x over 5 plus x squared over 25 plus x cubed over 125. What's your R in this one, guys? Look at this one right here. Look, what's your R in that one right there? And I'm gonna erase this down here so it doesn't confuse us on this problem. What's that? What's your R here?
X over 5.
Actually, at 1 over 5 you need 2, but you also need the X, don't you? It's X over 5. So the R in this case is X over 5. That's how we get from you get from 1 to X over 5 by multiplying by X over 5. X over 5 times X over 5 is X squared over 25, and so on. So my R is X over 5. So where does a geometric series converge? It converges where the absolute value of R, which in this case is X over 5, is less than 1. All right, well, let's talk about what that means. You got something that has an absolute value less than 1, that it means that it's in between 1 and -1. That's what it means to have an absolute value less than 1. It's in between -1 and 1. And if I were to multiply both sides by 5, I would end up with, or all through by 5 there, I'd end up 5 to -5. Okay, so if I plug in things that are in between 5 and -5, this thing will converge. It will diverge for x is greater than 5. Actually, for r's greater than 1. So in this case, absolute value of x over 5 greater than 1. Okay, it would diverge there, which is everywhere else. Because greater than 1, and this is where it diverges, this is where it converges, it'll be, this means, well, absolute value bigger than 1 means it's either bigger than 1 or less than -1. So that means that x over 5 is either bigger than 1 or x over 5 is less than -1. That's what that absolute value means. So that's or right there. We'll look at that in a minute, okay? But anyway, it converges right in there. And the sum is going to be a, which is 1 over 1 minus r. So 1 over 1 minus r, that's the thing where that power series converges and what it converges to. So if I said, what if x is 2? See, it converges everywhere between 5 and -5. If x is 2, I get 1 over 1 minus 2/5, which would be 1 over 3/5, which would be 5/3. That means that that limit of sequence of partial sums goes to that value. Okay, so let's keep looking here. Look at this one. That looks, oops, let's go down a little further. That looks geometric too. What's your R here, guys?
X.
X, yep. So this thing is going to converge the absolute value of R, which equal the absolute value of X, where it's less than 1. That means it's going to converge between 1 and -1. Okay. It'll diverge outside that range. 1 and -1 we're not sure about, but actually I think if you looked at 1 and -1, it may or may not converge at the endpoints there, but we'll look at that in a minute. So here, what do we have? What are we looking at here? If I said that the sum of that one is a over 1 minus r, then that's what the sum of it looks like. And that function right there this series is an estimation of that function. So for example, if I did put a half into it, I get 1 over 1 minus a half, which would be 2. What that says is if I put in a half all the way through this thing, like 1 plus a half plus a fourth plus an eighth and so on, if I kept adding parts onto this, in other words, if I kept looking at the sequence of partial sums, it would get closer and closer to 2, and we would say it converged to 2. Okay, so look at it and see what happens. If S1 is 1, we'll just get 1. S2 is the sum of the first 2. So 1 plus a half is 1.5. 1 plus a half plus a fourth is 1.75. Next one, 1 plus a half plus a fourth plus an eighth is 1.875. You can see the sequence of partial sums getting closer and closer to 2. Okay, so essentially we're going to talk more about this tomorrow, but this is a series representation of a function. I can figure out the value of that function by looking at whether the series converges or not. Okay, now there's some problems. You're going to say, well, why am I ever going to use that? There's some problems. In the first place I think of it is in differential equations, where you learn about at what rates things change. At what rate does a chemical change its form to different compounds or whatever, and those kinds of things can only be solved if you look at infinite series. Okay, they do have a use. All right, now nice thing about this is that we can test power series using the ratio test. It's easy to use. We've used it a little bit before. Remember I told you that if you saw a factorial in something, the ratio test was a good test. This can be used on a power series. And what you're going to do on the power series is the same thing you did before. We're going to look at the limit as n goes to infinity of x to the n plus 1 over x to the n, except that your book refers to it as u to the n plus 1. Oops, not m. U to the n plus 1 in here. Ah, shucks. U to the n plus 1 over u to the n. And the reason they change it is because we're not just looking at a single x anymore. We're looking at a whole nth term, and I'll talk to you about that in just a second. But by the ratio test, if we take the limit of this thing, we know this thing is going to converge if absolute value of x is less than 1. So between -1 and 1. So it'll converge for a half or a third, but it won't converge for 2 or -3. So essentially what you're looking at here, guys, is something right in here between -1 and 1, it converges, but out here where x is bigger than 1, that's a place where x is bigger than 1, or absolute value of x is bigger than 1, and out here is a place where absolute value of x is bigger than 1 because you're less than -1 there. So it would diverge in there. So the only place it's going to converge is right in that interval right there. And again, we're not sure about the endpoints. We're going to have to test the endpoints in a different way. All right. So that's my next thing I was going to say was if you consider the endpoint 1 and -1, if you looked at this one right here, the endpoints here, that converges for the absolute value of x less than 1. So x between 1 and -1. We know it diverges outside there, but if we plugged a 1 in here, look what your sequence of partial sums would be. 1, 1 plus 1, 1 plus 1 plus 1. That stuff just it won't converge. It diverges. So you do not have convergence at 1. If you look at -1, what it does is alternate. So -1 to the 0 will be 1. -1 to the 1 will be -1. If you look at the sequence of partial sums, the first one will be 1. The next one will be 1 minus 1 or 0. Next one will be 1 minus 1 plus 1, which will be 1. Then it goes back to 0. So you got 0, 1, 0, 1, 0. It fluctuates. It oscillates. So it does not converge at these particular endpoints.
Is that like n equals, is that a 0 or a 1?
It's a 0. I've started, you can start them at 0 or at 1, depending on what you're trying to do, but typically we're going to be starting them at 0. You can't start it at 0 sometimes if you've got an x in a denominator. For instance, if this had been 1 over x, we wouldn't want to start it at 0 because we don't want the denominator to be 0, but if you can do it either way. All right, now let's do some examples. Here's what the ratio test says. We're going to look at this limit as n goes to infinity of un plus 1 over un. That's an n, guys. Okay. And we're going to see if that thing is less than 1. If it's less than 1, the series is going to converge. If that limit's bigger than 1, the series is going to diverge. If it's equal to 1, even though in that last case I showed you it didn't converge at either one, we're going to have to test endpoints separately. So we'll leave that to kind of the last thing we do. All right, let's do an example. You want to know for what values of x this thing converges, and then you'll know what it diverges for. This ratio test easy to use because lots of things start to drop out. And I called this is what I called my UN. It wasn't just an A sub n because it has an x in it. That's just why we call it UN instead of AN. If you put in this top thing that goes in right here is UN plus 1. The bottom thing that goes in is UN. I am going to do that right here, n plus 1. Everywhere there's an n in the top, I'm going to put in n plus 1. So I put an n plus 1 in the place of n. I put an n plus 1 in the place of n right there, and then 5, and n plus 1 right there. Then I'm going to divide it by un. And un is just what it is. It's that thing right there. So that's un plus 1. That's un. I need to find the limit of this, or where the limit will exist or not exist. So once I get it like this, I'm going to invert and multiply because you're dividing by this. And you know what, guys? I don't even care. A lot of times you can kind of skip this step because you know this bottom one's going to invert and get multiplied by it. But now let's look at how it simplifies because that's really important. What's 5, first of all, what's 5 to the n over 5 to the n plus 1? 5 to the n over 5 to the n plus 1. Both powers. Say it again.
5n. I don't know.
Well, yeah, I tell you what. Let's look at it a little easier. What if I split this up? Isn't it true that 5 to the n plus 1 is 5 to the n times 5 to the 1? So what happens to the 5 to the n's?
Oh,
Yeah, they cancel. So guys, anytime you see something like this, if I'd had n over and the n plus 2 here, you could have rewritten it as 5 squared. It would have been 1 over 5 squared. So the 5 to the n's cancel right there and just literally leave me with 1 5. Okay, so that's what happened right down there. I've got a 5. Now, let's look at this one. What's x to the n plus 1 over x to the n? Remember, you subtract powers, right? This is x to the n times x over x to the n. What do you get when you combine those two?
X.
Yeah, just x. If you think about it as subtracting powers, you subtract the power on the bottom, you'll get n plus 1 minus n. It's just x. So that's where that came from. The last one is n plus 1 over n. And that didn't go anywhere. It just is what it is. N plus 1 over n. So I got n plus 1 over n. And then there's that 5 right there. And then there's the x. Now, I probably should have put another step in here. But let me see if you can read past my scribble and see what I did. Let's just look. The only thing that's changing here, guys, is the n. So I'm letting n go to infinity. If I let n go to infinity, where does n plus 1 over n go? And ignore that for a minute. Where does n plus 1 over n go?
To infinity.
1.
Well, no, well, be careful now. Remember, if that has the same power in the numerator as it had in the denominator, it goes to 1. It goes to 1, doesn't it?
1.
Okay, I see.
Yeah. And then what's left in the bottom is the 1/5. So that's how that 1/5 got down there. All right. And the x is still there. X doesn't have anything to do with n. It's just what I want to know something about what x has to be in order to converge. So I was looking at this part right here, and I saw, well, that thing goes to 1. That leaves me with 1/5 x there. All right. So here's the thing. There are no more n's in that. So what's its limit? What's the limit of any constant?
Constant.
It's just that constant, isn't it? It's just that thing. So once you let your n go to infinity and see what it does, you're left with something with an x in it, which is nice because we know by the ratio test that this thing will converge if whatever you get here is less than 1. So we know it, and it'll test absolute convergence because we were looking at the absolute value of all this. And if it converges absolutely, that means it automatically converges. But what happens here is that's what that is. Now, I'm going to multiply both sides by 5, and I'm going to get this. And then I'm going to say, okay, this converges between 5 and minus 5. Converges between 5 and minus 5. So everybody okay with that? That's the first conclusion. When you get to this point right here, you're going to do 3 things, really. 2 things. Initially, you're going to say if it's less than 1, that's where it converges. The next thing you're going to say is if it's bigger than 1, it diverges. So if this thing is bigger than 1, that's where it diverges. So it diverges. Now, get your absolute value stuff straight. Absolute value of x is bigger than 5 if either x is more than 5 or less than minus 5. For instance, if you took the absolute value of minus 6, would be 6, and that would certainly be bigger than 5. Okay, so let me kind of show you what we've got so far. I'm going to go down to the bottom for a second and don't worry about what I've got right there now. But so far, here's what we know. This series converges for all x's between minus 5 and 5. I know it converges there because that's where the absolute value of that thing was less than 1. It diverges on the outsides. It diverges on the outside. Now, we got one more thing to do. That's the easy part. And this next part isn't too bad. What we want to do now is we've got to check the endpoints separately. In other words, we got to check these 2 points right here to see what happens with them. Okay, so what I'm gonna go back and say right here that we must test 5 and -5 separately, because I'm not sure what happens at those kind of points in between the divergence and the convergence. All right, here's what I'm going to do. I'm going to go back to the original series. I got to test 5 and I got to test -5. And what I mean by that is this. Let me scroll back to the original series. There was the original series right there. I'm going to put in a 5 and I'm going to put in a -5 and see what happens. And then they'll go back to the kind of things you were testing in the section before. So let me do that. If I put in a 5, it'll be 5 to the nth over 5 to the nth. So you see what I did there? I put in the 5. It's 5 to the n over 5 to the n. That's going to go. And what's the limit as n goes to infinity? Oh, sorry. What's the limit? Yeah, as n goes, what's the limit as n goes to infinity? Actually, I'm going to ask myself, does this thing converge or diverge? Well, remember the nth term divergence test? The nth term divergence test says if this doesn't go to 0, it's going to diverge. Well, where does n go?
Infinity.
To infinity. Okay, so it diverges by the nth term divergence test. So what you're doing, again, what you're doing here is testing the endpoints. Is like testing the series you had in the previous section that didn't have any x's in them. All right, let's look at the next one. I got to test -5. All right, if I test -5, I'm going to put -5 in here. Well, let's look at that one. That's -5 to the nth. I'm going to write it because it looks better to me and lets me do a little more. If I write, this is like 1 times 5 right here. So I'm going to raise, it's like -1 times 5, sorry. So I'm going to raise the -1 to the nth, and I'm going to raise the 5 to the nth, all right? And then what's going to happen is I'm going to cancel the 5 to the n's again. Now, look at this thing. If you let n, what you end up with is -1 to the nth times n. That's an alternating series, guys. But remember, in an alternating series, this thing still had to go to 0. N doesn't go to 0 as n goes to infinity. I mean, an, that doesn't go to, that goes to infinity. So that diverges by the alternating series test. Okay. So what it says is this thing converges only in this interval right here, and it does not include any of those endpoints.
So my question is, we have to do this every single time?
Yeah, if you're gonna find out where power series converge and diverge, actually sometimes it's easier than others though. Let me spell it out and look at a couple more examples. But yeah, in the homework in 11.6, your instructions are to find the interval of convergence. Now, the interval, I got a couple of definitions for you, but the interval of convergence here is from -5 to 5. In this problem, that's what's called the interval of convergence. Now, I could have all kinds of intervals of convergence. I might have a bracket on this and a parenthesis on that, or vice versa, but you got to test the endpoints to know whether you got brackets on them. If it converges at any one of them, you're going to put a bracket on it.
And if it had like a bracket, I'm just speaking like if it had a bracket, it wouldn't go past the number, right?
Right. It would go to that number and include it. You know for sure that anything to the right of 5 and to the left of -5, it diverges. You know that for sure. You're only not sure about these, so you have to test them separately. I mean, let's do another one. Let's do another one. So what I'm showing you here, guys, is that that's where this thing converges. We call it the interval of convergence. And what's halfway between -5 and 5?
0.
0. We say here, guys, that's the interval of convergence, and we say it's centered at x equals 0. that interval at the center of that interval is 0. There's a reason for that too later on. I'll tell you what that is. All right, let's try another one. All right, here's one. I want to know where this thing converges or diverges. And it looks like this. If I let n be 0, x to the 0 and 0 factorial are both 1, so that's 1. By the way, in case you've never seen that, this is a little weird, but it's for all kinds of reasons. 0 factorial is defined to be 1, and it doesn't make a whole lot of sense. You say, well, factorial counts things down, and there's nowhere to go from 0, but that's a definition. Okay. So the next one, if I let x be 1, it'll be 1 over 1 factorial. Then it'll be x squared over 2 factorial. The next term will be x cubed over 3 factorial, and so on and so forth. Now, I'm going to use this ratio test to find out for what values of x that thing converges. So I'm going to take this thing, I'm going to put in, everywhere there's an n, I'm going to put in an n plus 1. Everywhere on the bottom, I'm just going to put that in, put that series in. So this is u sub n plus 1 over u sub n. I'm going to now invert and multiply, and I'm going to start simplifying. X to the n plus 1 over x to the n is just, daggone it, made a mistake, is just x. All right, does everybody see that? I don't know why I put that there. Because the x to the n's cancel out and you've got an x to the 1 left. How about n factorial over n plus 1 factorial? Remember how it counts down? It starts with n and counts down, and this one starts with n plus 1 and counts down. What's left?
N plus 1.
Just the n plus 1 down here. Remember we were talking about that the other day? This is n times n minus 1 times n minus 2 and so on. And this is n plus 1 times n minus 1. Everywhere past n, at n, you just end up with that n plus 1 down there. All right, so what we have here is this thing. I'm going to put in one more. It's like 1 over n plus 1. We'll leave the x in the absolute value. Where does 1 over n plus 1 go when n goes to infinity, guys?
Infinity or 0?
0, yeah, because the denominator is getting bigger and bigger, right? The power down here is bigger than the power up there. So that thing right there goes to 0, and we're left with the absolute value of x times 0. Now that's interesting, because it doesn't matter what the absolute, it doesn't matter what x is here, does it? Because anything times 0 is going to be what?
0.
0. And so we said that this thing would converge anytime this limit was less than 1. Well, this is always less than 1. So we say by the ratio test, if L is less than 1, this converges for all values of x. It doesn't matter what I put in here. This will converge. It will be a convergent sequence. And it's a really important convergent sequence, by the way, guys. And when a series converges for all values, we say its domain, or the place where the interval of convergence, is minus infinity to infinity. So far we've had one that converged on an interval. And now we've got one that converges everywhere because that limit went to 0. And 0 is always less than 1. So it converges for every value of x. All right, another example. We okay? I'm trying to give you an example of sort of everything that can happen here, and then we'll look at another one. All right, let's look at this one. Sum from n equals 0 to infinity of n factorial times x to the nth. I put in n plus 1 for the n's up top. Down below, I just put the n factorial x to the n. I simplify. N plus 1 factorial over n factorial leaves me with just a single n plus 1 there. X to the n plus 1 over x to the n just leaves me with an x. If I kind of like, sometimes you can always split this apart. The question is, what does n plus 1 do? What does n plus 1 do as n goes to infinity, guys? It goes to infinity. Well, you know what? It can't converge there, except there's one tiny little exception. It's not going to converge because that's never less than 1. unless x is 0. If that were 0, then infinity times 0 would be what?
0.
It would be 0, and that would be less than 1. So
Can you explain that?
yeah. So I don't care where this thing goes. If x is 0, then what's the limit going to go to? I mean, what's anything times 0?
0.
0. So the limit of 0 will be 0. Look, here's a better way to look at it. Look back at the series. Suppose you put in 0 for x here. 0 factorial is 1. 0 to any power is 0. The sum from n equals 0 to infinity is 0. It would just be 0 plus 0 plus 0. Okay, so it's going to converge to 0 there. Okay, so what that says is that it's also possible for a series to converge at only one spot. Now, the easy way to remember that, guys, is this. If this thing goes to infinity, that's the only thing that can happen. Whatever makes this 0 is going to be the place where it converges. It converges only for x equals 0. Everywhere else it diverges. Everywhere else it diverges. Just because 0 is the only thing that's going to make it less than 1. Okay, so I'll write that here. If x equals 0, then the limit as n goes to infinity of n plus 1 times 0 is equal to the limit as n goes to infinity of 0, which is less than 1, which means it converges at 0, but nowhere else. Nowhere else. Okay. So here's the big theorem that I've really been doing it already. But here's what it says. If an x to the n is a power series, then precisely one of the following is true. The series converges only if x equals 0. That's like the one I just did. In other words, everything went to it went to something like this: infinity times the absolute value of x. And the only way it's going to converge if x is 0. It converges absolutely for all x. That's the one I did right before the last one, where it went to, it was always less than 1, where it was 0. So it converged everywhere. And then the other time is when it converges when the absolute value is less than some number r. Like we had one that said absolute value of x is less than 5. So there's only 3 things that can happen. Converges there at a single point where x is 0, whatever makes this 0. It converges everywhere, or it converges on a small interval. So I gave you an example of every one of those in the previous 3 examples. I want to do another example, but here's what we're saying then. Plus or minus r. So if this is where it converges for absolute value less than r, so that would be where absolute value of r was less than 1. So that would be, well, that's not, well, for whatever the interval is. You'll see what I'm doing with that in just a second. Remember, we had a 5. My r would have been a 5 there. So in between minus r and r, it diverges outside those places. And then you have to check the endpoints separately. This is what I did with 5 in a minute. The interval of convergence could be any one of these things. This would mean that it didn't converge at any one of the endpoints. This would mean it converged at the left endpoint, but not the right. This would mean that when I tested the endpoint, this one converged there and did not converge there. This would mean it converged on the interval and at both the endpoints. All right, let's do another example. This is a theorem that's in the book. Does anybody need to hold on to that for another few minutes? All right, let's look at this one. I want to know what the interval of convergence is. So I'm going to use the ratio test on it. I'm going to put an n plus 1 right here in the top, and I'm going to put the n down below. I'm going to invert and multiply. I'm going to realize that x to the n plus 1 over x to the n is just x. And there's that stuff right there. Stuff with n in it. Now, tell me where that stuff with n in it goes as n goes to infinity. It's the square root of n over n plus 1. Where's that go, guys?
Infinity.
0.
Well, get your limit up under the root. If there wasn't a root there, we got a theorem from Calc 1 that said the limit of a root is the root of the limit. So what about n over n plus 1? Where does it go?
I don't know.
Well, yeah, you do.
One.
Look, here. Yeah, it goes to 1. Look, if I told you this, if I said, look at this, what's the limit of that? You'd say, oh, well, the powers are the same, so it goes to whatever the coefficients are. Okay? How about it? What if I'd said this? N squared over 2n squared minus 3. What would the limit as n goes to infinity of that thing be?
Oh, a half.
A half. That's all I'm doing here. I'm just taking those things. So, and the square root of 1 is just 1. So that's what that limit is. So what that says is, now this thing is going to converge. I took the limit. It's going to converge when the absolute value of x is less than 1. That means it's between 1 and minus 1. So far, I know it converges in here. It diverges out there. I have to check the endpoints separately. And guys, they're not hard, no, not necessarily that hard to check. So let's check the endpoints. So if we know if we need to add convergence on, need to add either one of those endpoints on where it converges. So suppose I test 1. Let's test x equal 1. In other words, what I'm going to do is put in 1 right there and see if it converges for that single value. So I get 1 to the nth, which is just 1. 1 to any power is 1. And I get 1 over n to the 1/2. What does 1 over n to the 1/2 do, guys? What kind of series is that, please? P series. When do P series converge?
When it's greater than 1.
It's greater than 1. So what do you know about this one?
Less than 1.
That diverges. Yeah. So we are not going to include that endpoint right there. We are not going to include that endpoint in our interval of convergence. All right, let's look at let's test minus 1. I got to test both endpoints. So I'm going to test minus 1 right there. Now, look at this. This is interesting. What kind of series is that, guys?
Alternating.
It's alternating, isn't it? All right, let's talk about alternating series. All right, this is an alternating series. The alternating series test says we look and see whether 1 over root n goes to 0 as n goes to infinity. Well, I think that's pretty easy to see. If n gets bigger and bigger and you got a root down here, it's going to 0. So it checks on the first thing. What's the second thing I've got to show by using the alternating series test?
If it's decreasing.
Yeah, if the function is decreasing. So if I looked at 1 over the square root of x and wrote it as x to the minus 1/2 and differentiated it. Remember we said we could do this by looking at the derivative. I think that's the easiest way here. It'd be minus 1/2 x to the minus 3/2. That would be minus 1/2 minus 1/2 over the square root of x cubed. Now, let's talk, x is really an n here, guys, because we only care about n equal 1 to infinity. And the square root, any number cubed that's positive is going to be positive. Square root is going to be positive. This thing's going to be negative. If the first derivative is negative, what have you shown?
It decreases.
It's decreasing. Okay, so the two things hold about the alternating series test. So this one right here converges for this one. That one converged, that one diverged. Now, let me show you something here, guys. If you look at a series that converges and its absolute value doesn't, that's called conditional. That's another good example of a conditional convergence. If you look at a series and it's with negative terms it converges, but when you take the absolute value it diverges, that's conditional. But the whole point of this that I'm doing right now is that the interval of convergence, it includes the -1, but it does not include the 1. So those are the values of x that you could plug into that power series and it would be convergent.
Are you saying that the negative, when we plugged in negative, that's the conditional,
Say that again.
the absolute value of like the second, like
Yeah.
input,
Yeah,
that's
look.
conditional?
Yeah, this is an example of conditional. If you have an alternating series or a series that's got negative terms in it, and it converges, but its absolute value doesn't, then we say that is conditional. It has conditional convergence. It does not have absolute convergence because its absolute value did not converge. That's an example of conditional convergence, okay? But it did converge, but the problem was that its absolute value didn't converge. That's why it's called conditional. All right. It's time. I'm gonna hold on this, guys. I'm gonna narrow down your homework for tonight, which will give you time to work on your quiz. As far as your homework, we have not gotten to this part right here. You can center power series at somewhere other than 0. I don't want to talk about what it is, but I can tell you the ones for the homework you're going to be able to do. And I encourage you to try a few of these so you know how to use this test. I'll talk about it again tomorrow. On page 572, see, my assignment sheet didn't last one day. 1, 3, 5, 7, 13. 1, 3, 5, 7, 13. They all have powers of x to the n in them, and that's what we're looking for there. Some of the other ones do and some don't, but anyway, those you can do. 1, 3, 5, 7. You could also do 9, but whatever. I'm done. Whatever. Any one of those you should be able to do. Test the interval, test the endpoints, and get me an interval of convergence. So we'll finish this up tomorrow. Okay. Who's got a question? Anybody? That's a lot, but the ratio test is not hard to use. So I think if you practice it a few times, you'll get it. If you have questions about those, now I've put those homework problems due on Tuesday. I won't put them due until late tomorrow afternoon. So if you've got questions about them during class, we'll do that first thing in class. If there's something you don't understand what I'm asking or what you need to do, a hint about a test, maybe I'll give a hint, maybe I won't. But I won't have that homework due until late, tomorrow night, whatever. As long as I have it before the next morning, before Wednesday morning. Okay? Everybody okay with that? You know which, I'm talking about the quiz that's on 11.5. Okay. Are we good? Deborah, can you walk?
Sort of.
Sort of. You're in the same situation I was the first of the semester. Now all I get to do is sit. I can walk now, but I can't sit. I can't walk because I got to sit all day. All right. Everybody good? All right. Did you pay your cousin, Alexis?
Yeah, I didn't want to, like.
But she did a good job, so you need to pay her.
She did. But I was there for a long time.
It's all right. That's what you wanted, isn't it?
Yeah, but
it takes a long time to get great. Okay. Isn't that right, Dion? How long did it take you to learn how to dribble? Not very long, I bet. Because you were playing with your brothers, right? Yeah. Okay. They wouldn't let you take too long. Bye. See y'all tomorrow.